Acidity comparison based on electronegativity and electron density. This video assesses your ability to apply electron density and electronegativity arguments to predict the relative acidity of organic compounds and your ability to use that understanding to predict the direction of acid-base reactions involving organic acids and bases. This quiz is a little different from the others in this series. I'm going to give you a short introduction and then follow that with a series of comparisons. It's meant to be taken after you've studied the material and think you understand it. During the presentation, you'll be asked to pause the video and try to solve the problem yourself, absolutely without looking anything up, and only then continue. It won't be hardly as effective as you jump to the solution immediately or use a table of pKa values from your book. Okay, here we go. This is a line that goes from -10 pKa to 50. It stretches across basically the entire range of acids possible at all, organic or not organic. Strong acids are on the left in the -10 to 0 range. Common weak acids are in the range roughly 3 to 12, and very weak acids are in the range of about 14 to 50. So, quick, name 6 strong inorganic acids. I will give you 15 seconds while I hum the Jeopardy song. Da-dum, ba-dum, 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 ba-da-da-da-da-da-da, ba-dum, bum, ba-dum, bum, 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 bum. Okay, how did you do? Strong acids. What do we got? Name one. Did I hear HCl, HBr, HI, H2SO4, HNO3? What's another one? Common one is HClO4. Okay, these are the strong acids. They are fully dissociated in water. That means that if we have water plus any of these acids, that will go to H3O plus and the anion, for example, Cl minus, exclusively, 100%. Essentially no equilibrium at all, irreversibly. Those are the strong acids. Okay, now, here we go. On the pKa line below, place the following structures where you think they belong. You can obviously do this in your head if you want to, but I actually would recommend on a sheet of paper, starting with drawing this full line from -10 to 50 and start entering them yourself. You'll find that by doing this by hand and not just in your mind or not just watching me do it, you actually will learn this much better. So pause the video. Think about where you want to put those. Do not, I repeat, do not look these up on a table of pKa's. Maybe you know them, maybe you don't. We just want to see where you're thinking they might go on this graph. Okay, we're back. Well, let's start with water. I bet you know pretty much what the pKa of water is. It's 16. Ammonia, not know, is about 38. A very weak acid. We're not talking about Put an H on ammonia, like you might have done last year with general chemistry, thinking of ammonia as a base. We're talking about ammonia as an acid. We're talking about ammonia going to NH2 minus plus H plus. Okay, and methane marks the far right end of our graph. Methane, pKa, nothing gets harder to take a proton off than methane at 50. Okay, that's fine, but the real question is, why? See if you can write down a sentence that says why these are in this order, with methane, the least acidic, then ammonia, and finally water. I'll just give you a few seconds to do that. Okay, if you said that, well, oxygen is more electronegative than nitrogen, and nitrogen's electronegativity is greater than carbon, and so oxygen holds on to its electrons more tightly than carbon, you're on the right track. Because if an atom holds on to electrons, that means it'll be easier to remove a proton. But I have a challenge for you. See if you can explain that without using the term electronegativity. Or actually, basically, I'm going to do that for you. Okay, so here's something you may not have thought about. I don't know if you learned this in class or not. I'm going to share with you an explanation that does not use electronegativity. It's one I really love. Let's start here with the CH4. You have a carbon, 4 hydrogens, right? Electrons almost evenly shared. But I want to think about these a little bit differently. I'll leave 3 of them like they are, but let's think of this carbon as being a carbon, sort of a carbon plus with 2 electrons. And what this H is, this is actually not an H atom. It's just the nucleus. It's a proton. That's what it is. H is equivalent to a P plus. All right, so what we have is 2 positive charge centers, 2 electrons in between, and it's these 2 electrons in between which are holding, pulling, attracting this proton to keep it in the system. Now here's something kind of cool. What happens if I were to take one of these protons that are out here on the carbon, and I'm going to say magically, but actually it's more like nuclear physics. We're going to take this proton, which is the hydrogen atom, and we're going to stuff that into the carbon nucleus. I'm not saying you can do this. I'm just saying we're going to think about doing this. All right. Well, what happens when you do that is that that carbon becomes a nitrogen. Nitrogen has 1 more proton than carbon. And what's left over here on the left is a pair of electrons, the lone pair on ammonia. Well, what happened over here? Is it the same? We still have 2 electrons. We still have the proton that might be pulled off. But check it out. Because that proton just moved from way over here to the nucleus, it's much closer to the proton in the center of the molecule. So what happens is all of the electrons get pulled toward the nitrogen. And that includes these electrons that are in this bonding situation with the proton. Basically what happens is the proton becomes exposed. That means more easily removed, and that means more acidic. Have you got that? Start with methane. We take one of the protons, we stuff it in the nucleus. using kind of a magic nuclear reaction, all of the electrons become closer to the nucleus, including this pair that's attached to the proton. The proton feels much more of a repulsion to the nucleus, and the result is that it's more exposed, it's more easily removed, and it's more acidic. And the amount by which that manifests itself is 12 pKa unit. Well, I think you can do this yourself, but I'm just going to point out that if we were to take the same thing with nitrogen, think of this as another pair of electrons and a proton out here. Here's our proton of interest, 2 electrons in a bond to it. And now we're going to take this proton and we're going to stuff it into the nucleus, and it's going to become oxygen atom now with another lone pair. And same story again. And now actually it's huge. This is now a 22 pKa difference. The idea here is that you do not have to use electronegativity as a crutch. You can understand this in a much more basic level just by thinking about protons and electrons and repulsion and attraction, and you've got the whole thing. All right, here we go. Now what we're going to do is take a look at this line with its reference values of water, ammonia, and methane at 16, 38, and 50 on the pKa scale. And my question to you is now going to be to place structures where you think they belong on this scale. It does not matter if you get this right or wrong. The question is, what do you know right now at this instant that would give you some sense of where these might be? Think about what you've learned. Give it a few minutes. Place them where you think they would be. Sketch them in with a pencil. Pause the video while you do that. Okay, ready to go? How'd you do? I'll just write them in here and we can talk about them. Ethanol is basically the same as water. There's not a big deal. Instead of having an H and another H on oxygen, we have an H and then a CH2 and a CH3. It's at 16. Acetic acid has an extra carbonyl group, and it turns out that pushes it down to 5. Now, hopefully you guessed that. The basic idea is that we have this other oxygen. It's electronegative. It's pulling electrons toward it. That's reducing the electrons in this OH bond and pulling the electrons toward the oxygen, exposing that proton, and it's easy to remove it. Trifluoroacetic acid then is going to be somewhere over here. No reason you would know where, but you should be able to think about the fact that the fluorine is really electronegative, and we have 3 of them. And so it's basically an electron suck, which is pulling electrons toward it all through these bonds, and exposing that proton significantly. And it should not surprise you if trifluoroacetic acid ends up right at 0, right on the edge of strong acid. We would consider trifluoroacetic to be a strong organic acid. Okay? So, similarity to water tells us the ethanol is going to be about the same place. The acetic acid has this extra carbonyl group pushing it down, and it turns out that's worth about 11 pKa units and puts it down at 5. And then adding this induction effect over here with the trifluoro brings it down another significant way. Now I want to point out that it's not just induction in terms of this carbonyl group, because you know there's a resonance contributor here that gives us this picture, and that's a clue that we've got extra repulsion from that oxygen atom on that proton. And this is a resonance effect that is predominant here. That's actually why it's so far 11 units. The other effect over here, where we have the fluorines, this is called an inductive effect. Okay, want to try some more? Okay, here we have them now. We now have 6 on our graph. Methane, way over there at 50. Ammonia in the very weak acid range, 38. Water, also ethanol, very weak acids. Now we have our first weak acid, acetic acid, and trifluoroacetic acetic acid, touching on the strong acids. Okay, two more. Ethene and ethyne. Where do you want to put those? Go ahead, see what you can do. Come back, pause the video. All right, welcome back. Here we go. There's no particular reason you know where these are going to go, but I'm going to show you, and then we're going to talk about them. Ethene comes in at 44, and ethyne comes way over here at 25. All right, what's the big difference? You probably know this. The key word here is hybridization. It's the difference between methane being sp3, ethene being sp2, and ethyne being sp. And the difference there is that we have basically 25% S character on the methane, 33% S character on the ethene, and 50% S character on the ethyne. And that is going to mean that since the electrons in the s orbitals are closer to the nucleus, these electrons in ethyne are being held much more tightly. And because the electrons are being held tightly, what they're doing is they're exposing this proton out here, calling the hydrogen atom. I'll write it as a P plus now. We're exposing that proton and making it more acidic. And ethene is just in between those two extremes. All right, here we go again. Here are three compounds I want you to put on the graph where you think they might be. It doesn't have to be exact, but give it a shot. See where you think these might be based on what you know about what affects electron density. Pause the video, write this down on your chart, and I'll be back in a few. Okay, we're back. How'd you do? I bet if you looked at this compound, you'd say that's an awful lot like the ones I have already here in the middle near water. And indeed, cyclohexanol comes in at 17, just a little bit less acidic than ethanol. Now, what about this phenol here? That benzene ring, you know, has resonance contributors that put a plus charge, formal charge on oxygen. Well, it shouldn't surprise you at all if it's over here, more acidic than cyclohexanol. And in fact, it's right around 10. And then what happens when we add this nitro group to the aromatic ring? Well, as we saw before, that allows for many more resonance contributors and in fact pulls that acidity all the way up to a pKa of 7. The effect we're seeing with this benzene ring is primarily a resonance effect. And the effect that we see with the nitro is a combination of resonance plus inductive effect. That's pretty much what I want to say. And what I would just remind you of is that it's not about memorizing numbers. It's about learning how the electronic nature of a compound affects its acidity. And you can do some really nice practice on this, just taking two compounds out of this chart, comparing them the way I was doing, where they're related compounds, and seeing if you can give a rational explanation for why they appear where they appear on the chart. The effects you're looking for, the explanations you're going to make involve the elements, carbon, nitrogen, oxygen. What is the atom attached to the hydrogen? Hybridization. Is it sp3, sp2, or sp? Inductive effects. What other electronegative atoms are in this molecule? And resonant effects, where you could draw a resonance contributor that puts a plus charge somewhere near that proton that's being removed. A plus charge was going to be attracting the electrons in the bond, repelling the proton, making it more easily removed. Now I've got a few more compounds I could throw on this graph and ask you to explain, but I'll let you do that on your own. Main point is that not all comparisons are possible. It wouldn't make any sense for me to ask you, for example, what is the difference in acidity between ethyne and cyclohexanol? None of us could do that. But when you look at pairs that are closely related, you should be able to come up with an explanation for why one is more acidic than the other. And if you can do that, the payoff is going to be absolutely huge for you. And as a bonus, this little chart that we've been making, this pKa line, turns out to be especially handy if you're considering acid-base reactions, because the acid on the left of the pKa line will also be the acid on the left in the favored equilibrium equation. If you're a visual learner, this is going to be a fantastic boon. Basically, if you can remember that this acid was on the left on this chart with a lower pKa, then you can remember that it's going to be on the left in the chemical equation that reflects the favored reaction. Nothing more than that. Find the two acids, compare them, and make sure they're in the right order, and you'll have it. All right, well, I hope that was helpful, and I hope you got it.